Pessoal, só agradecendo, né, a gente vai ter o colóquio, eu agradecer o professor Maurício, que vai fazer a apresentação do Rudorff, que trouxe e está responsável pelo Rudorff, então, nosso querido André, fazer o procedimento.
Boa tarde, obrigado pela presença, obrigado, professor. Alguém fez inscrição para ganhar o certificado? Alguém vai? Mais alguém? Não? Se alguém quiser ainda se cadastrar, o QR Code está lá na televisão, e pode me procurar no final da palestra, tá bom? Então vou passar a palavra para o professor Maurício.
It's my pleasure to introduce you Professor Rudorff from Germany. He's from Kassel University. He's a fellow, a PRINT fellow, so he's coming here thanks to the PRINT program at UCL. And Professor Rudorff, he got his PhD from UCL, and I don't know if I got something wrong. I got something wrong. So, and he did postdoc. Was that afterwards with Anatol?
Yeah, that was with Anatol.
With Anatol from University of Basel and then University of Vienna.
Yeah.
And then he has his position at University of Kassel since 2022.
22.
22, oh no, yeah. Since 2022. And he's going to talk today about quantum alchemy, which is, I found to be a very, very interesting subject.
Yeah, thank you very much for this kind introduction and for having me here. Today, I'd like to discuss a concept that probably many of you are unfamiliar with, but maybe is interesting food for thought to develop what we can do. So, quantum alchemy, that's no accident. We're actually going to change nuclear charges, but let's first take a step back and consider how we look at chemical space or chemical design. And typically, we could ask, isn't this kind of solved computational chemistry? I mean, we started doing this 1927, so almost 100 years now. And in principle, the idea is the same. You always start from a system. You think about which physics is relevant to your particular system in question. You come up with a Hamiltonian. And then from then on, Schrödinger's equation tells us how to proceed. So we get our wave function, and we can investigate, we can query this wave function using operators and get our property, right? So basically solved. Now the problem is twofold. One is the scaling of the solution. Looks nice and neat as long as you drop all the indices that it depends on. And the other part is the search space. So for the wave function, you know it depends on all positions of all electrons. So for anything amenable, for anything interesting, this is crazy large and complex. And I'd like to convert this into energy. Right? These days, everything is about energy. So let's think about how expensive it is to solve Schrödinger's equation with some reasonable degree of accuracy without any hard approximations. You can roughly estimate this. So if you want to do methane, that's going to set you back about a shot glass of fuel. If you want to do the N2 dimer, this is an FCI CBS estimate for the experts. That's about a barrel of fuel. And if you want to calculate the electronic structure of ethanol, then the energy for that is roughly what fits in a tanker. So, of course, we're not doing that. And computational chemistry is very good in finding relevant approximations. So to say, give you an idea, high-quality calculation is roughly a drop of fuel these days. But nonetheless, the search space that we deal with, chemical space, the set of all possible compounds that we might want to investigate, which might have interesting, relevant properties, is just terribly big. Typical estimate for synthetic databases of how many relevant molecules you have is about 10 to the 60. And now, even if we convert everybody on Earth into a brilliant chemist that can look at 1 million compounds a second and generously round up how many people we have, that still leaves about 10 to the 26 ages of the universe just to go through the list of molecules, right? We didn't even do anything with them. So that's unfathomably large. And for those of you who do materials, there's another estimate how many materials there might be. And even if you limit yourself to FCC only for tiny systems that are highly ordered because you only do a handful of primitive cells, you already see the number of systems easily approaches 10 to the 20, 20 to the 30 without much effort. So the search space is huge. Let me put up a little bit of a provocative statement. Speed doesn't really matter. So whether you make your DFT method 10 times faster, whether you make your algorithms 100 times faster, it basically pushes the exponential wall a little bit, but not much. The search space is still too big. So what I would like to argue is that it would be nice if we had methods that don't look at individual systems, but rather in regions in chemical space. Because this plot is going to show up more frequently. I'll explain it a little bit. Every point, every blue dot here is a system, material, a molecule, anything that you care about. So all of them together form chemical space. The blue dots are the ones we didn't do. And the orange ones are the ones that we actually calculated. And the traditional pictures, we can maybe afford a few points. That's how we did computational chemistry for decades now. What I think would be helpful is we found methods that allow us to look at regions, volumes of chemical space with one calculation rather than only individual points. I will argue that quantum alchemy is one such family of methods that might help go in that direction. So what does it do? The main idea is the realization that the electronic structure of similar things oftentimes is very similar. So if you ever did computational chemistry, then you're probably surprised by the fact that almost all of the electronic structure is kind of obvious. Right? It's dominated by the fact that you have an atom somewhere, so the electron density around that atom is basically almost the same. You now change something very far away in the system, there is a little bit of a response of the electronic structure, but it's not tremendous. So it's not fundamentally different. So the hope is that maybe we can treat this perturbatively. We can say we have our system, say a big molecule. Now we change part of that molecule. For example, we replace a functional group. And we would hope that then the electronic structure is largely similar. So we will treat this perturbatively. I brought you a system, and to not discriminate between people who do molecules or materials, we have a system which consists of 3 blobs. Now you can change each of these components individually. Right? That would be the cases here. You change the first one, you change the middle one, you change the last one. Now you can say, well, this is kind of a response function, right? And property of my observable changes, whatever I'm interested in, energy, for example, dipole moments, Moulomb gap, whatever you care about, changes by going from this one to that, to this one, to this one. That gives me derivatives. If you come from conceptual DFT, you call this response functions. If you come from the perturbative picture, it's derivatives in the mathematical sense, not in the chemistry sense, but the object is the same. And now you can combine those derivatives and say, well, if I change 2 things at once, then it's the sum of the 2 derivatives, because I changed both. Right? That's the simplest approximation that you can make. And now you can change 2 things, you can change 3 things, but it's a mathematical derivative. If I can go forward, I can also go backward. Now, if I do that, that's the blue changes. I can do the reverse change of that one. I will show you what I mean by that in a second. And that opens up a lot of different combinations that I can do from just a handful of calculations. Mathematically speaking, the way this works is you do a Taylor, you build a Taylor approximation where you say I change I have a multi-dimensional Taylor approximation, or you can do a partir approximation, which is numerically a little bit more stable, but those are technical details. The main thing is, this is a simple closed form expression. Right? In each of those predictions is a linear combination of this. If I have all of these things calculated, all of those are very easy to obtain if you just, if you're very careful about your index implementations, but that's a different story. So the one thing is the number of systems that you look at is combinatorial with the number of things that you can change. Right? If I have more and more options, then for more and more sites, that scales combinatorial with your problem size. And the other part, any prediction is very cheap, and I will come to that later. It's also a closed form expression, which you almost never have in computational chemistry. What you do SCF calculations, you do DFT calculations, couple cluster, MP2, doesn't really matter. Each of those methods have an iterative procedure, which means there's no closed form expression and you can't look at individual terms. So how does this relate to looking at regions in chemical space? Well, this is how I started. And the idea is, let's not do many small calculations that we can pay for. Let's do, for a given system, one calculation, which also includes the derivatives. So if you look at your system, you can build your Hamiltonian, and the Hamiltonian depends on 4 things in most cases. The nuclear charges, the nuclear positions, the number of electrons, and your spin. Now, some dimensions of those are more interesting than others. Why is that? Because, for example, the number of electrons almost always is pretty much the sum of all nuclear charges, because most systems are neutral or a little bit charged, but you won't have something which carries a lot of additional electrons. There's also, you can show that this would be not stable regardless of the system size. So this usually has a handful of values. This, the spin, also usually has a handful of values. So you can enumerate them. What is continuous is the positions. You can move atoms about in space, that's okay. And the nuclear charges. Now you might say, wait, what? Nuclear charges are continuous? Makes no sense. Well, in the lab, maybe, because you can only have integer nuclear charges for elements. But conceptually, Schrödinger's equation is perfectly fine with fractional nuclear charges. It's still valid because the nuclear charges only enter as external potential, and the external potential can anything you say it is. Which helps us because it allows us to go away from elements being discrete things and treating them as a continuous change. That allows us to do derivatives where we change nuclear charges. Yes, you can only experimentally look at integer nuclear charges. That's okay. But conceptually, this gives us one more thing that we didn't have before, namely a connection between elements. I'll show you that this helps machine learning, that this helps model building, that this helps in our Taylor expansion, in allowing to treat changes of atom composition in molecules and materials. So the idea is, let's calculate one system, and let's calculate the response functions with respect to the nuclear charges and to the positions. And we will assume that these things are fixed. That's why it's called quantum alchemy. And from a classical perspective, you may know this. Free energy perturbation calculations in classical molecular dynamics, for example, they use the concept of alchemy quite generously. But we look at this from the purely quantum perspective. So that's where the regions come from. We do one system, we do its perturbations, and then we can mix and match the perturbations to span a whole region in chemical space. And of course, I can say that up front, you can't do one calculation and then do everything, right? So this ain't gonna work because there's a Taylor approximation, so there's a convergence radius up to which you can do this with accuracy that is actually useful. But I will show you examples how big this radius actually is. Now, we did this for very many different things, and I would like to point out that this works for very many different things, even though the convenience of doing the individual properties might differ. So you can do this with a total energy, which allows you, for example, also to do interaction energies, because that would be the difference between total energies. You can do this with the electron density, or you can do this with orbital eigenvalues. So, for example, if you care about the HOMO-LUMO gap, that is differentiable and smooth. You can do this with dipole moments, which kind of makes sense, because if you can do the electron density, then anything which is a one electron property should work just fine. And I'll give you some more examples later on. The most complex we did is photoelectron circular dichroism. It's a very recent study where the idea is to really see and predict the interaction between the elemental positions and the circular dichroism effect. And what we're currently working on, which seems to work as well, that's why it's there in caveat, are NMR spectra. So you can have the shifts, the peak of NMR spectra, differentiate that with respect to the functional groups, which would help in identification. So you can say, I have a spectrum, I think it's this molecule. How would I have to change the molecule to match my spectrum more accurately? And we've tested this with a wide variety of quantum chemistry codes. So I would say if yours is not on it, we can probably add it quite quickly. All right, so mathematically, how does it work? So the idea is you choose an isoelectronic Hamiltonian because we decided to not change the number of electrons. Makes sense because energy, for example, is not differentiable with respect to the number of electrons, famously. So we have the one Hamiltonian, the reference, the one where we come from, and we have the target, the one where we're going to go to. The only different Hamiltonian, right? The only difference between the two systems would be that. So we introduce a linear mixing parameter. So if lambda is 0, you have the reference, and if lambda is 1, you have the target. Now, what you do is the regular Taylor expansion in 1D. You take your derivative with respect to lambda, and you integrate that, sum this up over the individual terms. So if you do this with the energy, there would be the energy of the reference, plus the change in nuclear repulsion, which is very easy to calculate, plus the sum of the different derivatives. And the different derivatives of the energy, in particular, you can express as density derivatives if you prefer that. Now, in principle, you might want to be unhappy with this, right? It's an infinite number of terms. But the hope is that, as with many Taylor expansions, that you can do this with leading orders only to get a workable accuracy that has sufficient predictive power. I will show you some examples of that in a second. Now you might say, wait, just because you make a Taylor approximation doesn't mean that A, converges. There's no guarantee for that. And B, that it converges to the right value. Again, there's no guarantee for that. So they're very nice examples of functions which do neither. So, but with a specific way of calculating derivatives, we can do this to, I don't want to say arbitrary order, but let's say annoyingly high order. And you see that the accuracy, this is the arrow that you see here, very quickly in the very first orders already is what we would call chemically accurate. So within 1 kcal per mole of the target DFT value. So this is from changing CO, carbon monoxide, into N2. Same number of electrons. I change 2 nucleosides at the same time, so I have C and O, and I make this N2. Or I go the other way around, N2, make this CO. You probably say, wait, this is by no means a small change. Why can I do a Taylor approximation? Well, the thing is, it's mostly dominated by the first few orders. And just because it so quickly converges, you can get away with a handful of orders. In practice, we usually do up to 3rd order, and that's sufficient. If you keep going, just As a side note, you can get several orders of magnitude more accurate than what you would usually stop at using your SCF iterations. So that's perfectly fine. All right, so now that we are happy with the fact that it does converge to something and it does converge to the right thing, let's see how far can we go. Because to make this relevant, we need to at least reach plus or minus 1 nuclear charge. Because otherwise it's a very nice academic exercise, but there's no practical value because in the lab you care about integer values, right? So we need to have a convergence radius of at least 1. This is an example, again, for N2. So you sit at nuclear charges 7 and 7. And we do our derivatives, and we see how far can we converge. That's the circles that you see. Basically, the bigger the circle, the larger the convergence radius. And you see that plus or minus 1 nuclear charge, that's what you see here. The small dots are the integer points, right? Plus or minus 1 nuclear charge is quite easy. And you can go substantially larger, sometimes beyond 3 nuclear charges, if you are very careful about basis set selection and how exactly you do the extrapolation. So there is a little bit of technicalities involved. In practice, we find that plus or minus 1 nuclear charge almost always works. Plus or minus 2 nuclear charges sometimes work. So how much does it buy us? Remember, combinatorially. If I can change n sites with plus or minus 1 nuclear charge, I can do 3 to the n different combinations. If I can reach plus or minus 2 nuclear charges, I can do 5 to the n combinations. That's very quickly a reasonably big number. So the moment you have a design space which is very small, it's probably not worth the effort. You can just enumerate it. But once you have a larger design space, starting from maybe 5 to 10 sites, that's a huge number of systems that you can all get almost for free, because all you have to do is calculate the weights in front of your linear combination. All right. Now, what kind of change can we make? I want to give one more example. You can create an atom. Let's start from helium. Helium has 2 electrons. H2 has 2 electrons. The isoelectronic. So based on the logic of the previous slides, I should be able to do that. But one has, well, 1 atom, the other one has 2 atoms. So what is the chemical change? The chemical change is to reduce the nuclear charge on the 1 atom that exists and create a new one. Which leaves me with the fun problem, I have to decide where to put it. I'm free to do that. It's just a change in external potential, which means we can do that in different distances. Which also means I can get the bonding potential, because I get an energy prediction for the energy of H2 for whatever distance I choose to grow my hydrogen atom at. And that's what you see here. I have a helium atom, and this is the bonding curve that I get from second, third, and fourth order derivatives. Why only second? Well, the first order derivative of this is a straight line, so it doesn't really qualify as a bonding potential. So you need something to curve, to have the potential curve back, so it would be second order. This is the second order prediction of the bonding potential. This is third, and this is fourth order prediction. The red dashed line is the truth. So there's an orange line behind that, you probably can't see that. So, which is quite funny, because we do the chemical perturbation of a single atom, we get a bonding curve of 2 atoms, just from the derivatives. All right, so much about the changes that you can do. Let's go to larger relevant systems. So here, for example, we have a design problem where we have a C20 fullerene. It's 20 carbon atoms, highly symmetric. And what we'd like to do is to predict all the energies of about 3 million targets there are. So there's about 3 million ways to replace 2 carbon atoms by BN pair. This you can still enumerate. I wouldn't say it's a fun undergrad programming exercise, but it is an undergrad programming exercise, right? So this is doable. Now, if you do that with quantum alchemy, you can exploit the symmetry, right? Because if I change one atom from a carbon to a boron to a nitrogen, well, it's the same change of different sign. But there's only, because they're all symmetry equivalent, there's only one first derivative, and there's only 5 second derivatives of the density because of symmetry. This is the 5 unique pairs you can have in C20. So if you do that, and then here you see the cost of running the calculation. Yeah, so if you want to do everything with couple cluster, it's going to be expensive. 3 million couple cluster calculations. And to give you an idea, this horizontal line is today on a supercomputer. This horizontal line is today on the university compute cluster. This horizontal line is today on a desktop. And you can say, okay, so couple cluster, fairly expensive, and then the ranking of the methods is fairly unsurprising. Our particular flavor of quantum alchemy that we used for that thing is roughly as expensive as a semi-empirical calculation. The catch is, it's slightly more accurate than MP2. So it sits around here in the accuracy, but about here, the cost. So in that case, it's about 80,000 times faster. You can do this for non-covalent interaction, where you say, okay, I have 2 coordinates. I would like, my design space is I want to be n-doped to 1 in order to maximize or minimize the interaction energy. What's going to happen physically? You change the external potential in the one coordinate, and that induces a mirror charge in the other coordinate because of the charge distribution, and that's why your dipole-dipole interactions of the 2 changes, which drives the change in non-covalent interaction energy. And that could be, for example, a design case where you say, I want to build a molecular sensor. Right? I want to be specific to one particular molecule. I want to be able to tell what that is. I want to trap a molecule. How do I have to change my surface such that my interaction energy with something else is maximized? Could be something where I do self-assembly, right? I want these things to stick together. I want to make sure that those don't stick together. So all of those interactions would follow basically this idea or this rule. So we wanted to maximize, minimize the interaction energy, and those are the resulting patterns that you see. So here this is maximally separated, and here this is maximally balanced. You can verify this where it's just fine. Here you can't enumerate this because this is 10 to the 10 unique ways to do so. So we use a genetic optimizer, still about 20,000 times faster than doing this individually. You can also get the electron density prediction. This is what you see here, because I mentioned that we can do the density derivatives as well. So this is the DFT electron density, and this is the quantum alchemy prediction electron density. You know those games for kids, right? 5 to find differences. So that's pretty slim. Now, up to here, this was a numerical prediction of quantities. I mentioned that we not only get numerical predictions, we also get a closed form expression. It's just a simple polynomial. It's a Taylor expander, right? So I have a polynomial. So I can start looking at the terms. Because in the expression, you have a response of the system and you have a change that you do to the system. So if there's any kind of symmetry in your system that you have, it turns out that there's also a symmetry in the response. And with that, I'd like to motivate a certain kind of symmetry. You all know rotational symmetry. Right? To take the same molecule and rotate it should be the same. You know chirality. So if the physicists don't listen too closely, then the energies are the same. But turns out that if you do this for alchemical changes, let me try to enlarge this a little bit. So you can see it better. So this is a benzene skeleton, and we do a certain change. We do BNNB doped. The same number of electrons, nothing has changed. We just changed the nuclear charges, effectively moved some of the charge over here. And we can do this in the opposite way, NBBN. Right? Those are the two chemical changes of opposite sign, right? The external potential. Now, it's interesting that if you look at the chemical derivative expression for that, at the individual terms, you can show that those two energies need to be almost degenerate. The first three orders of derivatives are exactly the same. So as you go from benzene this way or from benzene that way, the difference in energy up to third order is identical, which means that they need to be degenerate. You can look at it. Let's count the bonds. What kind of bonds do we have? We have here, there's an NN bond. There's no NN bond in this one, right? Here's a BB bond. So yes, the carbon-carbon bond is the same, but if you compare the two, you will see that they don't even have the same bonds. But nonetheless, pen and paper says their energy shall be the same. You say, I don't believe this, right? Let's look at something larger. This is naphthalene. Again, we do two changes, NB, NB, and the one in the opposite direction. And now you can plug this into your most favorite quantum chemistry code and choose a method that you think is reasonable. And if you do this with coupled cluster, then these are the energies that you get. So because of rounding, is actually less than 1 millihardsy difference between the two, which is much less than the actual accuracy of the method you have. Now you can't do this with arbitrary BN dopings. There's a rather complicated list of conditions that I will not mention right now, but the thing is that by looking at the pen and paper expression, we can identify a symmetry and we can exploit that symmetry. Why is that? Well, think about machine learning. In machine learning, I collect some data and then I build a model to predict me more data. And usually we include symmetries in our machine learning models. Makes sense, right? I don't have to train a model to tell me that the molecule here, and the molecule here is the same. I'm not going to add more and more training data just because, right? I'm going to tell the model translational symmetry is a thing. I'm going to tell the model rotational symmetry is a thing. So what happens if we tell a model a chemical symmetry, or a chemical non-symmetry, as how we called it, are a thing? That's what you see here. This is a learning curve. So this means this is the accuracy, the error of the model. Lower is better. And this is the number of training points that you have. And now you can either do this with symmetry or without symmetry. So with symmetry is orange, and without symmetry is blue. Now you may say, okay, yeah, a little bit lower, but basically looks the same, right? It's true, but keep in mind that this is log scale. So going from here to here is a factor of 2, which means I need half the training data for my space because I know of the symmetry. Now the symmetry isn't perfect, right? I said there's a small difference, right? We're talking about a fourth order derivative impact. There is a difference. And that difference you can quantify is about here. Which means that as long as my machine learning model is worse than that difference, I can just throw in the symmetry and save data. So that's exactly what we're doing in this case. I also mentioned that between the BN and D case, right, so the one from the previous slide, this one, that the bonds are different. The bonds are different. Now we can do what chemists did decades ago. We can count bond energies. Right? We can calculate, we can count which bonds on the one side, we can count which bonds on the other side. If you do that, turns out that from that symmetry follows this expression for the bond energies. So if you have 3 consecutive elements in the periodic table, QRS, then this symmetry, without any further requirements, says that this must be true for the relative energies of the different bonds. And you can plug this in numerically, works just fine. So this allows us to estimate bond energies just from the symmetry, just because we looked at the Taylor experiment, because we looked at the expressions. So if we mix that with machine learning, that saves us some data. Now, because, well, for recent events, I want to show you one fun example of what you can do with the symmetry without a single quantum calculation. So now all the results I'm going to present are just a consequence of the symmetry I mentioned of a chemical enantiomer. We didn't do any calculation. I mean, we verified this with calculations, but the statement itself has none. So what's the idea? We have Piscine. And now we would like to BN-dope this one. There's very many ways to do that. We looked at a chemical space that has about 400 million ways to do that. Those are the symmetry unique calculations or variations. Now, what can you do? If I have a chemical chirality, if I have the enantiomers, which I know need to have almost the same energy, I have transitivity. Right? If this molecule and that molecule need to have the same energy, but that molecule and the third molecule are also the same energy, this means the first and the third need also to be roughly the same energy. I get groups of molecules which need to have the same energy, only broken by nuclear repulsion. And we can use that to rank all those 414 million systems just based on what follows from the symmetry. And you can then analyze all those systems based on different properties. Let me enlarge this again. Let's look at maybe this one here. The BN bond counts per BN pair. Basically says, of all those systems, if I change them, are B and N right next to each other, or are they separated by whatever degree? And the x-axis is the rank and energy. That's what you see is, if you have few BN bonds, right? You're on that end, and that's well sorted. There's nice steps that you can see here, which are just based on the number of BN bond counts you have, which gives you a clear design request, what you need to do in order to make a molecule stable. Now, look at the next plot, the NN bond counts. You see there is an inverse structure. There's, amongst every step of this one, you have a new sorting in the total number of these bonds, which means that one of the two effects is stronger than the other. And that allows us to rank this conditionally in decreasing strength. It's basically first sorted by this one, then sorted by that one. So if you do that, then how do you make a BN-doped version of this molecule stable? Well, at first, you should add BN pairs. Well, there's very little surprise. If I collect my nuclear charge in one place, that should increase stability. So then you say, and next, we want to maximize carbon-carbon bonds. Then substitute at sites shared by the rings. Right? These sites, if you change something there, has a stronger effect. Maximize how many BN bonds you have in your system, and so on. So with this, you can find design rules for this chemical space without actually doing any calculations, just based on pen and paper. And this is where I think one of the strengths of the quantum alchemy approach lies, that yes, the individual prediction might be incorrect. Just like a quantum chemistry method, the individual calculation might be wrong. But because you can see each and every term, the aggregate data, the aggregate trends that you get from this, they should give human readable design rules that are actionable in actual design applications. So here we did millions of ones. The last example I want to show you is about the interconnection between nuclear degrees of freedom, so what are your nuclear charges, and the positions thereof. And this will be a hard test. Why? Because this is about a highly coupled problem. It's about the angular emission in DECD, so interaction between the charge distribution and polarized light. So depending on whether it's left polarized or right polarized, there is a slight difference in the response of chiral systems. And that response is what we want to model. That's the response is that we want to understand. And why is that? Because the calculations are terribly expensive. For that, you need to model the wave packet, the charge distribution response over time after the incident light. And that's inherently sequential. So I propagate the wave packet after the incident light, which means I can't calculate the final state. I need to do all the propagation in between. That's what makes it so expensive. So what is our system? Our system is a set of charge distribution, is a protomolecule, and you can model the angular emission with two parameters. The one that tells you how strong the effect is, and the other one which tells you how strongly it's anisotropic. We will model those two parameters, beta 1 and beta 2, separately. And effectively, this is now the multidimensional Taylor expansion. Right? So we have a property, the betas, which depend on a number of variables. That would be the charges of the individual protoatoms, and on the positions of those protoatoms. And this is a standard expression for the expansion up to some finite order k. Now, this time I want to focus on analyzing the individual terms. Right? So I said we get the individual expressions, we can get the individual derivative entries. So let's analyze them. Let's try to understand what is relevant for that system. Do we care what that charge is? Do we care about where the charges are? Do we care, is there an interaction between charges and positions? And that's exactly what we did. So first, the design question. So can we push the effect? That's what we did, just from one set of derivatives. Strongest effect that we had in the training data of the original system was 5.6%, so 5.6% difference between left polarized and right polarized light. We can push this to maybe 26%. And if you want to minimize that, right, you can go the other way. So we can make the difference negative, right? That's how beta 1 would be defined. There will be to about minus 15%. So the design prediction works, right? The trend. The number value is not perfect, right? So we predicted values which are a little bit more extreme than the actual calculation, right? That's true, but the trend is correct. But I mentioned the interactions, right? That's what we care about. We want to understand what is going on in each individual term, which one is relevant. How do we push this molecule, how we push a system to have a stronger response to polarized light? So what do we have in our system? We have charges, we have positions, and we have the energy of the incident light. Those are the degrees of freedom that we have that we can analyze. So let's group this, because otherwise there's so many derivatives, the terms, it's maybe not terribly easy to see what's going on. So everything which has a derivative with respect to a position, right, gets an R. If it's first order, it's R1. If it's second order, it's R2. Everything with respect to a nuclear charge gets a Q. And again, the same. If it's Q2, then that would be second order. And every term which has mixed things, so one charge as one position, one charge, gets R1, Q1. Principle clear? Because that's going to show up a lot in the plots. Which means that of all possible position derivatives, they all gather in here. Right? So if the position derivatives are relevant, then R1 is relevant. And that's what you see on the right-hand side. I will make this a little bigger so we can see this better. So the different colors are the orders. Right? With the Taylor expansion, we would hope that as you go to higher orders, impact gets less. Right? Otherwise, we have a hard time converging this. So that works out. Right? So fourth order down here, very small distributions. First order, big distribution. Okay. Now, what this is the distribution of how important these groups of terms are for the billion derivatives, billion changes to the system. That's why we get a fairly wide distribution of things. And we see, okay, so the energy of the incident light matters. Okay, very good, no surprise. Charges matter, positions matter, but you see that the distribution, the width of the impact is much smaller, right? So some things are more important than others. And this is the distribution that you see, and what you see in here is the variance of the data, so it becomes a little bit clearer, easily comparable. So, but what you see is that once you go to the second order derivative, it only pushes towards positive values. Right? Both beta 1 and beta 2 are only changed one direction. You see that, for example, the second derivative of the positions doesn't really matter. So the quantity that we have is not curved along the positions. It's good news, because there's so many different ways how you can change the positions, right? It's 3D, but there are much fewer ways how to change the nuclear charges. So if that thing is small and that thing is bigger, that's okay. And with that, you see that, for example, the spatial derivatives, also the other higher spatial derivatives, they're practically zero. But there are some interaction terms between the energy and the charges, which we can analyze individually. We can tell what needs to happen to the system in order to push the individual responses. And as I said, this is a billion different systems. There's no way I can ask my colleagues to run a billion calculations of these. That's exactly where the power comes from the derivatives. Now, because we have the terms and because we know the impact of each individual term, we can ask ourselves the question, so do I need it? Right? It's a multidimensional Taylor expansion. Every term that we don't calculate is a term we win. It's cheaper to not calculate something. So this is what we see in the plot over here. And I'm very happy about the way this plot turned out. So on the x-axis, we have the number of coefficients on logarithmic scale. Number of coefficients is also the number of calculations that I need to do in order to get my Taylor expansion. If my Taylor expansion has 10 coefficients, I need to have, well, 10 individual quantum chemistry calculations in order to get those coefficients. And on the y-axis, you have the error of beta 1, so the strength of the effect in percent. So ideally, what we would like to have is that everything which is expensive, so needs many quantum chemistry calculations, also contributes very little to the overall error if I just ignore it. And things which are cheap, they should be up here. So ideally, we have something that looks like this. Oh, wait. So I'm not hiding stuff behind the insert, trust me. So this is all just fine. It means that all the ones that happen to be expensive, mostly everything which is the higher orders of the spatial derivatives, because there's so many of those, everything which is expensive can be neglected. So if we ignore everything which has the crosses here, then this is the error we make. This is the actual value, and this is the approximation with the Taylor approximation. That looks pretty good. I can work with that. We can use that for design. So the suggestion is to keep everything which is a point in this plot and to neglect everything which has a cross. So we can tell which terms are relevant, and we can use that to build cheaper perturbation models of the same quantity. All right, now I was told I have about 1 hour, so I will use the last minute to tell a little bit about how far you can trust this. So what are the problems? So the first problem is this concept, if you want to actually calculate this, is somewhat unusual. So you have to arm wrestle quantum chemistry codes to actually calculate the quantity that you want. So it's not terribly straightforward. We figured out how to do this for a handful of codes I showed you earlier, but you can do this with probably most major quantum chemistry codes. And calculating derivatives is surprisingly hard. There are a few different ways how you can do that. There's the boring one, finite differences. Right? Just point here, point there, take a line, right? High school. Is hard to get numerically stable. Very reliable, very easy to implement, a very nice way to check your numbers, but not terribly exciting. You can use Hellman-Feynman derivatives. You can say, I'm just changing my Hamiltonian, so I evaluate my electron density with the new Hamiltonian, done. Those of you who do quantum chemistry probably know why Hellman-Feynman derivatives are not used, even though they're so cheap. They just also happen to be wrong, right? So if the basis set is not terribly converged, the derivatives maybe have wrong sign. So this is reasonably hard. You can do coupled perturbed derivatives. That's very elegant. Right? Your Szabo and Ostlund contains the correct equations for that. And problem is, you can only do this for first and second order, and it's fairly tedious to implement. You can do conceptual DFT, technically very elegant. As the name says, DFT, it doesn't work for Hartree-Fock or the post-Hartree-Fock methods. But a very modern thing, a gift from machine learning, is automatic differentiation, which allows us to, automatic differentiation, for those who are not familiar with that, is a way to treat the program, a pure function, as basically apply the chain rule to computer code. Any function you write is a sequence of commands which can be seen as a nested function, and you can just apply the chain rule to that. If you follow some rules and change the way you design code, you can use automatic differentiation on quantum chemistry. That's amazing, because you know how this worked previously. If someone decided, I want that derivative for my favorite functional, well, I've got to hire a grad student, wait 2 years. So this is much more convenient. It's a little bit slow, it's modern, it's very, very niche, but there's a handful of codes that can do that. Alanis Burguzik started this in 2018. It's the first paper ever on this. The postdoc who did that left academia. But there are a few more people trying that. Probably the most feature complete is PyCF80 and that thing. So that was probably the future on how to get those derivatives and other stuff. Now, the other problem from a quantum chemistry perspective is, well, when people thought about quantum chemistry, they thought of elements as being discrete things, which means that pseudopotentials, basis sets, everything are designed for every element to be independent from each other. That does make sense, but if you think about the fact that Schrödinger's equation is actually continuous, that would make fitting basis sets or pseudopotentials much easier if you use the derivatives as a constraint. Nonetheless, until that happens, we have to do extra steps to make that work. And then, of course, there's a finite radius of how you can push it. But think about a condensed system. Think I have a surface and I change all atoms on the surface. There's very many ways how I can do that. So that's easily in the order of millions. And that's what we typically see. Then we have the speed up even for molecules, which are much smaller, about 100,000. All right, And then in terms of convergence, some systems are easier to work with than others. So if you have symmetry, spatial symmetry in your system, you can exploit that, which gives you an additional bonus. So sometimes it's helpful to think about which point you choose to start your perturbation from. All right, so with that, I'd like to close. Thank all the colleagues who co-developed this, and I hope to have given you a few ideas on what you can do with quantum alchemy, and maybe food for thought that elements, at least theoretically, might not be as discrete. So the hope is that with that we can reuse calculations, that we don't need to do every system one by one by one, but that we can rather predict many things in one group. And we can use the symmetries to reduce the problem, right? If we know that this point and that point need to be the same, we can fold our search space and have fewer data requirements. And this being physics-driven, right, that has predictive power for extrapolation, because I know that this is a response in that direction, so if I go in that direction, that should be the answer. And that's helpful for design, because if I don't like the way my property changes in that direction, I don't have to explore it. Much more efficient to never look at something rather than to try to enumerate it. So hopefully with differential chemistry, we can push this further to get derivatives of more quantities and to get derivatives for more systems more efficiently. And we can look at the closed form expression. We can understand why the answer for a given system is that particular value, which terms contribute. We can analyze that, or we can use that to understand more of the physics. So with that, ultimately the hope is that we can look at regions in chemical space rather than points. Thank you.
So do we have questions? Yep. Thank you for your insightful presentation. My question is this. Okay, it's a question and again it's a comment too. This really looks a bit complex. I'm a pharmacist, very interested in drug design, drug discovery. So I'm wondering how will this help us in drug design? And again, even when you apply these the concepts, the principles you've mentioned here, again, you know, in drug designs, we design drugs, and you don't rely on your design outside the biological system. You still need to do your trials in the biological system, which introduces a lot of variables to the drug performance. A drug that might be effective based on, you know, in vitro design or maybe combinatorial chemistry or functional designs might fail in the biological system because of the complex nature of the biological system. So, is this truly a reliable method? Can this really assist in drug design? That's where I'm really concerned. And again, it's a bit complex. It's quite complex.
So let me address these two dimensions. So the one thing, the complexity, and the other one, can it help in drug design? Now, for the complexity, I think the main problem is to wrap your head around this idea we change nuclear charges. So once you get used to that, it's essentially the same way how you optimize the molecular geometry. When you optimize the geometry, what you do is you calculate the gradient, which is the negative of the force, and you go downhill. If you calculate vibrational spectra for IR measurements, well, that's a second derivative, but apart from that, it's exactly the same. So it's a standard technique to look at those derivatives. What people just didn't do so far much is to look at the nuclear charge derivatives or derivatives with respect to functional groups. So where this is most helpful is if you right now rely on quantum chemistry structures in any way. If you say, I design my system such that on a quantum calculation or a QMMM calculation, they fit in the pocket, right? If you say they bind to some receptor, right? So whenever you would use a quantum calculation right now, at that stage of drug design, then you might be able to use that, because that's what it's meant for, right? It's meant to replace the sequence, the long series of individual quantum chemistry calculation, each and every one starting from scratch again, by a more clever way, exploiting the fact that those calculations are very similar. This is not going to help with any other stage of the pipeline. So if you, your predictive power for in vitro efficiency is not going to change. So you can expect to get roughly the same mileage out of the result as the quantum chemistry method, like MP2 or DFT, for 5 orders of magnitude less compute effort. But you won't get anything beyond that. And the complexity, so the implementation of these high order Taylor derivatives is non-trivial, and that's to some extent where I see the responsibility of our group. So we make libraries available for that. My email address if you have any questions. But we make libraries available for that do exactly this. All you have to do is you have to be able to calculate the quantity that you care about. The quantity that you care about for a system, and for a system where you change something, and for a system where you change something else. If you can calculate these, the rest you can feed to our libraries and they will do the Taylor expansion. It's cheap because it's just a polynomial. I admit it's reasonably hard to figure out the prefactors, but that's it.
Again, in terms of the cost of the equipment to do this, really, it's also an issue. The cost of software and all that they're going to use too. I see this application in drug,
Yeah. The software is free.
So Sci4, the quantum chemistry code is free. Okay. PyCF is free. MRCC is free. Orca is free for academics. CPTK is free. CPMD is free. So if you start thinking about quantum chemistry in general and you want something which is free and reasonably convenient, I'd suggest PyCF. And that's open source, is reasonably well supported, and there is a flavor of PyCF which allows for automatic differentiation, which is going to be very helpful for future machine learning models and also for quantum chemistry, for quantum alchemy. And PyCF is well documented, pure Python. That's also what we use for most of our modern calculations.
Any more questions on the MRCC software? Is it a repetition?
Yeah. Sorry. Yes. It's the same. Yes. MRCC is from Hungary. Is a very is a high quality quantum chemistry code, especially for arbitrary order coupled clustering.
So, all the applications that you mentioned for your method revolve around molecules. But I'm thinking here that it might as well be very suitable for defects in semiconductors, for example, or defects in crystalline structures, where you could take, for example, boron in silicon or nitrogen in silicon. You could gradually change the atomic number of one silicon atom and simulate a substitutional defect there. Have you done that? And if you did, what kind of properties would you be able to infer by using a method? For example, the incorporation energy, the electronic characteristic of that defect, whether it's a donor or an acceptor, the lattice distortion that this defect would induce in your crystalline system.
So there is one quantum alchemy method that has been evaluated also by Georg Kresse from WASP. That would be the virtual crystal approximation. It's a very crude way of doing this. Basically, you mix pseudopotentials, so it's not exactly the physical derivative, but they have explored it, and that seems to work for stress tensors, for spatial rearrangement. So they had They had a crystal and introduced heteroatoms in there, which would be point defects, and calculated the corresponding energy of formation, the corresponding distortion, and the change of the lattice constant. Seemed to have worked for them. I would also expect, but this is helpful, is if you think about nanostructuring the surface. So what happens if you introduce heteroatoms at the surface and you have want to calculate, for example, surface protonation, you want to tailor interaction with molecules, you want to tailor energetic properties, for example, for water splitting applications. So I think that should work quite well. The catch is what we haven't figured out yet, so we ourselves, is how to go beyond the virtual crystal approximation for periodic systems. So we know how to do this in CP2K, which would be a classical materials code to do that. In VASP, it's not as straightforward, which is a side effect of the PAW potentials that they use. So in quantum alchemy, you would change nuclear charge, but in PAW, you have your pseudopotential parameterized by a parameter vector, and 3 consecutive elements are not on a line, which means there's a derivative discontinuity in that space. So in VASP probably is not going to get on this list for exactly that parameterization reason that they use for PAWs. CP2K, which doesn't use PAWs, but rather GTA pseudopotentials, there we know how to do it. So that's work currently in our lab, how to do that.
A bit more on that with the GT pseudos, you have a continuity between pseudo potentials that you don't have with.
Yes, because GTH, you have a functional expression, yeah, and you plug in parameters. With so PAWs, you have a discretized potential. So, yeah, yeah.
So for the virtual crystal approximation, we know that the results are less than impressive.
Yeah.
Right? For example, if you take an alloy, a silicon and germanium, you know that there is a bowing factor in the band gap prediction, whereas the virtual crystal approximation would give you a straight line.
Yeah.
So I was wondering if this method would be any different or more successful than.
Yeah, because you have the actual change in nuclear charge. And so in the virtual crystal approximation, you have your effective potentials, which are parameterized to work for the integer nuclear charges, but basically produce an ill-defined interpolation. I mean, you can, yes, you can technically take the parameters, you can calculate some weighted average, but there's no reason why that should impact the corresponding results. There's another reason why the virtual crystal approximation has a problem, because you don't have the spatial rearrangement, right? So you take your atoms and you make all of them a certain percentage of the mixture, and now, of course, now this has no local rearrangement because of the structure. How I think this should work is, imagine I have my system and I calculate the derivative of each and every site towards some chemical change, which means I can change each site individually. So if I have n atoms, and they're not symmetry equivalent, I have n derivatives. And now what I can do is, if I want to model 20% of some changed atom, I can generate a random distribution of 20% that atom, and I can use their chemical derivatives to predict geometry and the energy of that distorted geometry. And I can do this repeatedly for different atoms being changed, but with that stoichiometry. And that should be a much more reliable predictor of what you have in reality. The individual value for that, of course, because of the nature of this, is a Taylor approximation, might again be wrong, but the overall trend that you get from that as a collective response, I think should be more reliable. We yet have to test that numerically.
Yeah, okay. It's a fast one. Do you think that in this case it would be more time efficient doing this method that you just mentioned than just running the calculation itself?
Well, running which calculation?
You take, for example, 20% of an alloy element within a crystal.
Yeah.
It has several different configurations, and you think that would be time would be more efficient time-wise?
Substantially so, because you need one quantum chemistry calculation, right? As compared to however many you need in order to sample your distribution of 20% different random configurations. When I showed you this plot, this distribution here, right? This is 1 billion calculations. That takes about 5 seconds on this computer from 3 years ago. So the individual predictions, they cost nothing compared to any kind of quantum chemistry calculation.
I have a last question. Does anybody have a question? Okay.
That's very good. Keep asking.
Yeah.
Sorry, I think I didn't get. So the idea is you want to predict a certain property, or the idea is if you have this from the experimental side, then you can predict the material, the position of atoms. What's the goal?
So if I understand this correctly, the question is, do we want to go from property to find the system, or do we want to go from the design to predict the system? Actually, both. So if I have a way to make my quantum chemistry prediction of a property go much faster for small changes in the overall structure, I can use that to go both directions. For example, for NMR spectra, we want to improve the estimation. Right now, it kind of includes guesswork, right? That you say, I think it's this molecule, but I don't actually know. And that way, the hope is that if we have a system and we can calculate all derivatives, then we can very quickly and very easily test whether I can make my spectral identification a little bit more accurate by changing something in the system that I maybe haven't thought about. And the other thing is, if we do design, right? Imagine you have the surface and you want to have an electrode be sensitive to a small concentration of some other compound, then I would like to tailor my surface structure such that it binds that compound and it never lets go again. And so that would be like a design problem. And in both ways, it would be efficient. I think the best way to think about this is it's helpful if you have a large set of calculations that you would like to do, where each calculation has almost the same system, but not quite. That's where this is helpful. If you want to calculate millions of different systems, different size, different elements, not related to each other, that's not going to be helpful.
For example, you said about photoelectron circular diaphragm, and if you have something about photoelectron diffraction, you know it's possible to apply the methodology?
I don't know.
My question is related to changes when you change the number of electrons.
Yes.
Can you do it?
Well, what is that derivative? I mean, you're teaching quantum chemistry. That's yeah. So the problem is the total energy derivative is not defined. I mean, there's a derivative discontinuity. Maybe not in practice, but at least in theory, there's a derivative discontinuity, and that means there's no decent derivative to exploit. You can, so we played around a little bit with it, so you can kind of smooth over it, right? So if you can make it differentiable by just assuming it is, and then predict something. But I think it's not really worth the inaccuracy that you gain by this. And the reason why I think this is not worth the inaccuracy is the total number of electrons for a given system size basically only has a few number of values it can have, right? I mean, pick a molecule, how much negative charge, how many electrons can you still have bind to the molecule?
Yeah, but I'm only interested in, plus 1 plus 2 minus 1.
You can just enumerate this. So for example, when we calculate the deprotonation energy, I didn't show that in the application, but effectively, it's much easier to just take your system once with that number of electrons, once with the other number of electrons, and then derive both at the same time, which gives you the energy.
That's exactly right.
Yeah,
Can
I think.
that?
Yeah.
It works?
Yeah.
Well, let's thank again the speaker.